All right, 9.2, graphing rational functions. Now, a rational function you're going to see in the form of f of x is equal to p of x over q of x. Now, p of x and q of x, those are representing polynomials. Okay, so we're going to see, quadratic over a quadratic, or a cubic over a quadratic. All right, so one thing when it comes to these rational functions, q of x, which is in the denominator of the rational function, okay, that cannot equal 0. Okay, we cannot divide by 0, therefore the denominator cannot be 0. Okay, now that is what's going to cause what are called asymptotes. Okay, now an asymptote, okay, these graphs are going to look like this. An asymptote is going to be a horizontal or vertical line that our graph can never cross. Okay, we'll see those once we start graphing them. But a hyperbola now, so anytime I refer to a hyperbola, that is just going to be the graph of a rational function. Okay, so let's go ahead and let's look at them. Now, when we graph these, okay, we're going to use the parent function. Okay, the parent function is f of x is equal to a over x minus h plus k. And again, we will see that h and k like we have in the past. Now, h is going to represent our vertical asymptote, and k is going to represent our horizontal. Okay, now, anytime the parent function will look like this, and we're going to have two different branches to these graphs. Okay, so, and again, that's the parent function, which will be just y is equal to 1 over x, where we don't have that shift left and right, up and down with those asymptotes. Okay, so when we look here, what we're going to do is we're going to look to see what is going to make the denominator 0. So we're going to set the denominator equal to 0, and we get x is equal to 1. That is what's going to be our vertical asymptote. Okay, and then our horizontal asymptote we find with the k. So if you look at that 1, 2, just like we had before, now it's going to be a little bit different. Okay, this is what we're going to consider our new origin. Okay, here's h, there's k. Okay, so typically you would set, vertices or something like that when we did quadratics. Okay, but h and k in this case, 1, 2. Now we're going to consider that our new origin in this case. Okay, now that new origin is where our vertical and horizontal asymptotes go through. Horizontal and vertical meaning straight up and down and straight left and right. Okay, so now we said those are asymptotes, and before I had mentioned that those are imaginary lines, which is why we're going to dash them, that the graph of the hyperbola will never cross. Okay, so again, vertical asymptote, okay, a vertical line, that's always x equals, so in this case, x is equal to 1. Horizontal asymptote, or horizontal line, is always y equals because it's going through the y-axis, which is 2 in this case. Okay, now, when we do this, we're going to use an xy table. Okay, and we're going to represent x with, or y with f of x, okay, which is representing the parent function, which is y is equal to 1 over x. Okay, and the values we're going to use are -2, -1, 1, and 2 for our x values. Okay, now taking those values and plugging it into that parent function, you're going to get -1/2, -1 over 1, which will be -1, 1 over 1 is 1, and then 1 over 2, so 1/2. Okay, and then if you remember, you always take that a value times that column, which in this case is 3. So we're taking 3 times -1/2, which will be -3/2. 3 times -1, or -3. 1 times 3 is 3. 3 times half is 3/2. So if you remember, we ignore the middle column at this point, and then from there, -2, -3/2, that is saying left 2, -3/2, and before it was always from that vertices. Now we're going to go from that new origin. So in this case, we're going to go left 2, down 3/2, which is 1.5. Okay, then left 1, down 3, right 1, up 3, right 2, up 3 halves. And again, remember, it's always from the origin, the new origin. Now, what else you're going to notice is when we went right 1, you up 3. So when you go left 1, you have to go down 3. Okay, those points are reflected. Okay, so really, if you just found the left side, you'd be able to get the right side as well. Now, when you actually graph these hyperbolas now, we said that it should never cross the asymptote. So what you need to do is you're going through those points, and then as you approach the asymptote, you're going to get closer and closer and closer, but never cross. Now, one thing I typically see when making the hyperbolas is this. The graph should never come back. Okay, the further you go along the asymptote, the closer and closer that you should be getting. So by the time you get to the end of your graph, you should almost be hitting that vertical and horizontal asymptote. All right, so there's our graph. Now, for domain, again, domain is left and right. It's a lot easier to see the domain when you're given the graph. Now, it looks like it's going left and right forever, but there's one thing. We said we will never hit where x equals 1. Okay, so that's where the function does not exist. Because if we were to plug 1 into here, you got 3 over 1 minus 1, or 3 over 0, which we cannot do. So our domain in this case is we want to include everything except that one value. Okay, and what you're going to notice is that that value you're not going to have is always going to line up with the vertical asymptote. Now for the range, we're always dealing with y. We're going to y includes all real numbers except for that 2. So y cannot equal 2. Okay, and again, that range will always line up with the horizontal asymptote. All right, so that's the first example of graphing a hyperbola. So now, again, moving to another one, very similar to that. Okay, figure out your HK, which in this case will be 4, 3. And again, that's considered our new origin, 4, 3. And then from there, you can sketch out your vertical and horizontal asymptote. And again, just going left and right, up and down from that new origin. And now that vertical asymptote, that's up and down, which is always x equals, it cuts the x-axis in half at 4. And for the horizontal asymptote, y is equal to 3. Going ahead, doing our table, x, f of x, a f of x. Okay, again, -2, -1, 1, 2. And again, our parent function is 1 over x, so -1 half, -1, 1, 1 half. And again, those two columns will never change. So you can just go ahead and memorize those two columns, but better is understanding why. Okay, because if I wanted to do more points, I could do 3, and that would be 1/3. Okay, now we're not going to worry about that in this case, but a in this case was -1, so -1 times f of x, just taking that and basically flipping the signs for that column. So 1 half, 1, -1, -1 half. Okay, ignoring that middle column, -2, 1 half, that's saying left 2, up half, left 1, up 1. And I don't even need to go back to my table, because if I went left 1 and up 1, that means I can go right 1, down 1. Okay, left 2, up half, right 2, down a half. Now again, when doing this, I just start on one of the points, go through that other point, and then approach the asymptote, but never cross, and get closer and closer as we go. And then for both branches, we'll do that. Okay, so there's our hyperbola. And again, domain, x is element of all reals, such that x cannot equal whatever that vertical asymptote is, which is 4 in this case. And range, y is an element of all real, such that y cannot equal the horizontal asymptote, which is 3. All right, so that is graphing rational functions. Now, there's another form you will see. Okay, now in this form, there is no parent function that we can go off of, so it's a little bit different. Okay, for the horizontal or for the vertical asymptote in this case, again, we're setting the denominator equal to 0. And we're figuring out what x value is going to cause the denominator to be 0, because that is where our vertical asymptote, that is where the function does not exist. As for the horizontal asymptote, we are going to look at the ratio with x, okay, a over c. Okay, so let's go ahead. Let's say 2x plus 3 over 2x minus 1. Okay, if that was our function. Vertical asymptote, again, we're always setting the denominator equal to 0. So for our vertical asymptote here, 2x minus 1 is equal to 0. Solving for that, you get 2x equals 1. Oop. Give it a minute here. Okay, so again, we set that denominator equal to 0. So 2x is equal to 1, dividing by 2, x is equal to 1/2. That is your vertical asymptote. Now, this is where it's a little trickier on this one, the horizontal asymptote. You are just taking the ratio with x. So in this case, it would be 2 over 2 or 1. And whenever it is a horizontal asymptote, it is y equals. Okay. Now, finding those points for the graph will be a little bit different. We'll go over that here in this next example. So, again, first thing you always need to do, figure out your vertical and horizontal asymptotes. So in this first one, 3x plus 3 equals 0. We're going to set that. Okay. And then solve. 3x is equal to negative 3. X is equal to negative 1. There is our vertical asymptote. Okay, and then for the horizontal asymptote, we're taking the ratio of those coefficients with x. So in this case, will be 1/3. Okay. All right, now this is where it's a little bit different than the previous examples. Here we're going to use an xy table. Okay, and if we got our new origin here, we got negative 1 and 3. So we got that vertical asymptote at negative 1, horizontal at 1/3. Now, if you get a fraction like that, you just got to do a rough estimate of where it would be. Okay, but those are the vertical lines and horizontal line that we will not cross through. Okay, now for the x values that we're going to use in this case, what we're going to do is we're going to go 2 left and 2 right of that vertical asymptote. So if our vertical asymptote is at negative 1, we're going to evaluate negative 3, negative 2, 0, and 1. Okay, so those are the x values we're going to use. And what you got to do is you are just going to plug it in. Okay, so negative 3, that's saying negative 3 minus 2 over negative 3 times 3, which will be negative 9, plus 3, which will give us negative 5 over negative 6, or 5/6. Okay, for negative 2, that's going to be negative 2 minus 2 over negative 6 plus 3, which would negative 4 over negative 3, or 4/3. Okay, as for 0, that's saying 0 minus 2 over 0 plus 3, which is negative 2/3. And finally 1 minus 2 over 3 plus 3, which will be negative 1 over 6. Okay, now, what you need to remember when we're doing these ones these are actual points of the graph now. So for here, this will be -3, 5, 6. You're going to actually plot that point. It's not going from the new origin. Okay, for that next one, -2, 4/3, 0, -2/3, and finally 1 and -1/6. Okay, so -3 and 5, 6, left 3 from the actual origin, and up 5, 6, which is just about 1, but not quite. Okay, -2, 4/3, which is 1 and 1/3. Okay, 0, -2/3. And then finally 1, -1/6. Okay, now keep in mind, we should be that same distance away, like when I go left 2 and right 2 from that new origin, that up and down distance should be the same. Okay, and then again, go through the points. The further we go along the asymptote, the closer and closer we should be getting. Now, test or quiz time. If I see that you cross through the origin or through those asymptotes, that will be counted off of your graph. So make sure you are approaching it, but not crossing. All right, so for domain then, again, it's always going to be x includes all real numbers, but then excluding that vertical asymptote. The range was always y is element of all the reals, such that y cannot equal whatever that horizontal asymptote is. Okay, so a little bit different than the previous ones. A little bit harder because then we actually have, remember, you're doing an XY table, so those are actual points on the graph. Okay, we'll go ahead and we'll skip that one for today. Let's do it. Okay, senior class is sponsoring a dinner. The cost of catering the dinner is $9.95 per person plus an $18 delivery charge. Okay, we're going to write a model that gives the average cost per person. Okay, so when we are doing this now, you got to think about the total charges. Okay, so $9.95 per person. When we do that, you got to take $9.95 times however many people you have. So like if you have one person, it's going to cost $9.95. If you have two people, that's going to cost that $19.90. Okay, but then we also have that delivery charge of $18. That is a constant. It is not changing. Now, in order to find the average price, okay, that's the total price right there. Is it $9.95 times however many people you have plus that 18. In order to find the average price, you got to divide by how many people you are going to serve. Okay, so there is our model, and we'll say P of X. Okay, the price depending on how many people eat. Now, we're not going to worry about graphing or describing what happens, but that would be the model for that situation. Again, $9.95 per person, so that's where we get the 9.95x plus that delivery charge of $18. And to figure out the average, you got to divide by that x, or how many people were eating that dinner. All right, so that is 9.2. Your homework is 9.2 homework. Okay, go ahead, you can skip that problem, but identify your vertical and horizontal asymptotes, match the function, okay, and then actually graph a few of them there in both forms. If you have questions, let me know. Otherwise, have a good day.